Hey, welcome back to Critical Thinking. Last time we took a look at Mill's methods, which were experimental methods designed to try to identify causes. We're going to move away from experimental science this week and we're going to focus on what we call historical science. But we're also going to spend a little bit of time dealing with some causal reasoning, specifically mistakes in causal reasoning. Let's get started. Now that we're moving away from experimental science to historical science, it would be tempting to assume that we don't have to concern ourselves with present observation and experimentation as we dig into the past, but that would be incorrect. In fact, let's briefly review the difference between experimental science and historical science before looking at why experimental science is essential for doing historical science. As you recall, the scientific search for causes can be divided into two basic categories: empirical, which deals with present experimentation, observation, and events, and historical, which deal with events of the past, where there is no direct experimental data. And since all science is based on empiricism, I prefer to refer to the first as experimental science. But both approach their targets and measure their views against the regular pattern of events observed in nature. So the key to the scientific approach remains observation, even though much of what we deal with in science is itself unobservable, such as subatomic particles, very small things, and very big things. Historical science merely deals with those unobserved events of the past. Now, because of this, you would assume experimentation could never play a part in historical science, but that isn't actually true. Experimentation here and now in the present can be very useful for those working to reconstruct past events. Even historians themselves have worked with scientists to create experimental reenactments of events to test historical hypotheses, addressing questions like how the Egyptians moved the stone blocks into place in the pyramids, or how the Greeks produced red or black figure vases, or how fast or long a man could run wearing 70 pounds of hoplite armor. Numerous disciplines fall under the heading of historical science, and here are just a few: forensic science, paleontology, archaeology, historical geology, cosmology, and the list can go on. The historical scientist seeks to reconstruct a comprehensive and consistent picture of past events, and such a reconstruction must be based on two core principles: that of causality and that of analogy or uniformity. The principle of causality states that every effect or better event has a cause. Effects are things that are caused, so that is tautologous. Or we could say everything that begins has a cause. Note that the principle does not say that everything has a cause. Nothing happens without being made to happen by something else. Nothing comes from nothing, so the ancient adage goes. And you should never make the mistake of confusing ignorance of a cause with lack of a cause. That's the general principle, and it's one of the assumptions of science. Now, like so many things we've studied, we can divide causality into two types. We can speak of natural causes, where causality is attributed to the ordinary patterns or laws of nature, in other words, non-intelligent causes, and agent causes, where causality is attributed to a purposive will, goal-directedness, something we might call an intelligent cause. I think this example should make it obvious. When you look at this stone, it has natural cause written all over it: erosion. But this stone? Not a chance. We wouldn't mistake it for a product of natural weathering. This is the product of an agent, and a very skilled sculptor at that. Now, what about these two? It's a bit trickier, but I think it's fairly intuitive. There are actually numerous signs if we know what to look for, and we don't really need to look very hard when it comes down to it. And since we did it with causality, let's do it with causal explanations. We'll divide them into two kinds following our two types of causality: physical causal explanations, following our natural. Physical refers to the domain of the natural sciences, explanations for events and phenomena as to their material background, and behavioral causal explanations following agent. Behavioral refers to the domain of psychology, sociology, economics, and other social sciences. Explanations that attempt to elucidate the causes of behavior with reference to reason, motive, goals, habits, etc. Behavioral background includes the general conditions under which a behavior manifests itself. Experimental science deals with present regularities, situations and phenomena that normally and repeatedly occur, because they're governed by the laws of nature, as we find in physics, chemistry, etc. Experimentation and hypotheses and testing methods can be utilized because we're dealing with occurrences happening in the present which are readily observable, but this is obviously not the case with past events. Here, we're dealing with past regularities or singularities, situations and phenomena that may or may not have repeated occurrence, singularities being unique and neither observable nor repeatable, and either type being the result of natural or agent causes that were governed by those same natural laws. Though the events themselves are unobservable, the effects may still be seen and studied, and often the processes can be reproduced in the present, like in archaeology, or the processes may have a present continuation, as we find in geology or astronomy. The key to understanding causality in these situations is going to be the principle of uniformity. We studied analogy some time ago, so it might be helpful to review it just a little bit. Analogy is similarity between like features of two things which enables comparison, or an inference from one particular to another particular. In historical science, an analogy is drawn by comparing the present with the past. The principle of uniformity says that the present is the key to understanding the past. The basic assumption is that the same causes operating in the present were operating in the past, and our knowledge of how the universe currently operates allows assumptions as to past events. Remember that this is a common inductive tool. The analogical argument begins by drawing an analogy between two or more things, and it can focus on one or more similarities between those things, then concludes that the things compared are alike in some respect because they're alike in other respects. This type of argument is the basis of taxonomy, upon which all science depends, and taxonomy is the practice of classification. The principle of uniformity is an argument by analogy, and it's not only employed to understand the past according to the present, it could be employed to make predictions of the future based on the past and present. We presented the general form of the argument somewhat like this. A, B, C, and D all have characteristics P and Q. P and Q we call the basis of the analogy, the similarities. A, B, and C all have characteristic R. A, B, and C we call the ground of the analogy. That's our sample, the things that are similar. Therefore, D probably has characteristic R. D is the objective extension, the target of the analogy, and R is the problematic extension of the analogy, the feature that we have in question. Now note the word probably. It indicates that this is not a deductive argument. And to wrap up this review, here again are the 6 evaluative criteria. Number 1, the greater the ground of the analogy, number of things compared, the stronger the evidence for the conclusion. 2, the larger the basis of the analogy, number of similarities, the stronger the evidence for the conclusion. Number 3, relevant factors contribute to the argument more than numerous irrelevant similarities. 4, disanalogies, or differences between the ground and the objective extension, weaken the argument. 5, when the ground and basis are strong, differences among objects in the ground can strengthen the evidence. And 6, the stronger the conclusion, the greater the burden on the premises and the weaker the argument. Perhaps you recall this analogy regarding the possible purchase of a motorcycle. All 5 of my closest friends bought motorcycles so they could ride across country together this summer, and all of them purchased their bikes from the same cycle shop across town. They're all unhappy with their bikes. I was thinking about going to the same dealer, but now I think that if I do, I'll be making a big mistake. If you want to walk through the 6 criteria as we evaluate the strength of an argument, go back and check out episode 18 where we did just that. Or try this analogy on your own as practice. The 10 vases I threw in the workshop and subsequently broke, and every single attic potsherd I analyzed from the British Museum all have the same surface characteristics as well as cross-section markings. This Neolithic potsherd, which dates to around 6000 BC, has very similar features. I know the vases I produced were thrown on a mechanical wheel, and the potters of ancient Athens also used the wheel in pottery production. It seems like this Neolithic pot was wheel-made as well, but this runs counter to everything we think we know about early handmade pottery. The Neolithic artifact is a very small fragment, but I'm certain it comes from a wheel-made pot. Now, let's turn to everyone's favorite pastime, identifying fallacies, specifically those that have to do with causal reasoning. A fallacy, remember, is a mistake in reasoning. And we've already studied 3 of the 5 major types that we'll come across in this course: informal fallacies of ambiguity, relevance, and presumption in general. The 4th we covered briefly, but we'll now revisit in more detail, which are fallacies of presumption and inductive reasoning, including scientific fallacies or fallacies of presumption in causal relations, committed when mistakes are made concerning, guess what? Causal relationships. And the 5th major type of fallacy is found in formal deductive logic. The following inductive fallacies were introduced back in episode 19: biased generalization or sample, hasty generalization or conclusion, anecdotal evidence, self-selection fallacy, weak analogy, and vague generalities. I'll leave it to you to check that episode out for a complete overview. Here, we're going to concern ourselves only with mistakes in causal reasoning, and our first fallacy is going to be a familiar one: the post hoc fallacy, which has already been discussed as a reductive fallacy of presumption. It's often referred to as the fallacy of false cause, so it naturally falls under the umbrella of scientific reasoning with its concern for causal relationships. Of course, false cause doesn't point to the exact error, as most of the other causal fallacies could be similarly named, since the common theme here is misidentifying or confusing causes. The actual name is short for post hoc ergo propter hoc, after this, therefore because of this, which is much more descriptive: the fallacy of identifying something as a cause that is not a cause due to assuming a causal relationship based on a temporal relationship or a relationship in time. It assumes a common antecedent factor as the cause. The related cum hoc ergo propter hoc, with this, therefore because of this, makes the same mistake with concomitant factors. Here's a lame example. The farmer believed the sunrise was caused by the crow of his rooster, because every morning the rooster crowed and it was immediately followed by the sunrise. Second, we have the problem of emphasizing irrelevant factors. As we just said, it's easy to confuse concomitant factors with causes. It's a case of oversimplification and overemphasizing the significance of a factor that is insufficient or irrelevant. Assuming a common factor is the cause is often due to not using the joint method. For example, it's no surprise that a country guaranteeing a citizen's rights to gun ownership has a problem with violence. Next is the inclination to neglect negative evidence, the tendency to overlook instances where the supposed cause does not produce the effect, or to ignore evidence that's unfavorable, which likely stems from our human propensity towards confirmation bias and loss aversion, given our commitment to our pet hypotheses. But this is something Mill's negative method of difference was designed to correct. Fourth is neglecting differences, mistaking similar antecedent factors for causes, or ignoring differences in causes and assuming that similarity is in fact identity. For example, Jesus' emphasis on the Messianic kingdom and his animosity towards the religious leaders in Jerusalem is similar to the concerns and views of the Essenes, so it's clear he was a member of that Jewish sect and his teachings grew out of theirs. Fifth is reversing cause and effect, confusing an effect with a cause or vice versa. Now, how's that possible? Well, cause and effect are not temporal relations, as those who commit the post hoc fallacy often assume. It's often difficult to establish which factor has some type of priority in many situations. And there is an aspect of the cause-effect relationship that is simultaneous. Think of a brick breaking a window. We imagine the brick is first and the broken window follows, cause then effect. But in actuality, the brick is not a cause at any moment prior to the breaking of the window. The cause occurs at the same time as the effect, the brick simultaneously trying to occupy the same space as the glass and failing. To illustrate reversing cause and effect, we could go back to our farmer and rooster example, as the crowing is a response to something the rooster senses before the farmer does. Another example could be this. The students with the highest GPAs are those studying Latin, so studying Latin produces smarter students. Sixth, not considering reciprocal causality. This is a mistake of assuming that causality is always unidirectional, when it might be bidirectional. For example, violence in video games and on television causes violence in society. Seventh is confusing cause and condition, or better, confusing necessary and sufficient conditions. A condition may be necessary for an effect, but a cause is necessary and sufficient to produce that effect. There's a difference between something being needed to set up an effect and something making an effect occur. For example, high cholesterol causes heart disease. Well, high LDL cholesterol may be a condition for the development of heart disease, but it may not even be necessary. And it certainly isn't sufficient on its own, and this is the reason that doctors emphasize cholesterol as a contributing factor rather than an outright cause. Eighth is ignoring possible common cause. This mistake occurs when we think X caused Y, when in fact both X and Y were caused by some third thing, say Z. It's related to the correlation error which we just mentioned, cum hoc ergo propter hoc, with this, therefore because of this. And I've already said this many times in past videos, but correlation does not equal causation. Imagine this causal explanation. Ice cream sales are up because people are wearing bathing suits. I would love to see a study tracking the ice cream eating habits of people leaving indoor swimming lessons in the dead of winter. Most people just assume the increase in both may be the result of hot summer temperatures. Or we could err in the other direction in assuming a common cause. It's basically discounting the possibility of coincidence. So in that, it's similar to the post hoc fallacy. When two events happen in some proximity, it would be a mistake to assume that they have the same cause without good evidence or reason. For example, I find it rather suspicious that John F. Kennedy, C.S. Lewis, and Aldous Huxley all died on November 22, 1963. There has to be some Soviet involvement here. 10th is confusing conditional probabilities. If you test positive for bladder cancer and the test is 90% accurate, what's the probability that you actually have bladder cancer? We have to be careful not to confuse cause and effect. Testing positive for a medical condition is an effect of having the condition. If a test for bladder cancer is 90% accurate, then 90% of those who have the cause, bladder cancer, will have the effect, a positive test result. To determine the probability of having bladder cancer, you actually need to know two additional things. One, the percentage of people without bladder cancer who test positive, what we call false positives, and two, the frequency of bladder cancer in general, which we call the base rate. If, let's say, 10% of the people without bladder cancer test positive, and the base rate of bladder cancer is 1%, then out of every 1,000 people on average, 10 will have bladder cancer, 9 of them will test positive. 990 will not have bladder cancer, but 99 of them will test positive. So out of every 1,000 people, on average, 108 will test positive. And out of the 108, only 9 will actually have bladder cancer. If somebody tests positive, the chances of having this condition are not 90%, but 8%. Next, we have overlooking statistical regression, or regression to the mean, which refers to a statistical property of measurements of mean values of populations, where if a data point of a random variable lies excessively outside the norm, future data points will tend towards the norm. If you take one measurement that tends towards an extreme, the next measurement is likely to be closer to the mean. For example, if the average mean height of a 40-year-old man is 5'10", the average height of the children of fathers over 6'4" will be closer to 5'10". In other words, the children of unusually tall fathers are apt to be closer than their fathers to the average height. This is also why casinos make money. Anyone can get lucky and win, or even land a winning streak, which is very addictive. But if someone plays long enough, their luck regresses to the mean, and on average, more people lose. It's also why the music industry has so many one-hit wonders, artists who hit the top of the billboards. It's very rare to remain in that space for long. The average artist never makes it big, and it's a small portion of artists, about 20%, who actually account for the majority of the greatest songs, about 80%. Now, why is this? Well, the explanation does not involve cause and effect, as fathers of unusually tall children are also apt to be shorter than their kids. Obviously, this cannot be explained by cause and effect, since children don't have any influence on their parents' genetics. Regression to the mean usually occurs because of a sampling error or an abnormality, often the result of too small a sample or a biased sample. We already know the importance of randomization. If we don't use random selection, our results might trend abnormally high or low. Even using random selection, there's a chance of hitting that abnormal data point, but at least here our data is going to regress back to the mean. Hence the importance of random selection and control groups in experimentation. When running medical drug tests, for example, it's necessary to use both, because without these safeguards, we can't conclude from the fact that a remedy was followed by an improvement that the remedy caused the improvement. The improvement could just be statistical regression. 12th, we have proof by absence of disproof, which is essentially the same as argumentum ad ignorantiam, the idea that the absence of a disproof counts for the probability of a hypothesis. Nobody has proven that homeopathic remedies don't cure X, Y, or Z, but failure to disprove a causal hypothesis only leaves intact the reasons already present for thinking the hypothesis is on the right track. It doesn't create a new reason for thinking so. Next is the problem of confusing explanations with excuses. In our modern political climate, it's not uncommon to assume that anyone who tries to explain the cause of something like an atrocity is trying to excuse the atrocity. An explanation is not the same thing as an excuse, and it doesn't entail some type of moral stance. For example, people trying to explain the attacks on 9/11 were accused of trying to justify those attacks, and this led some people to dismiss the causal explanation. To assume without reason that the speaker must be trying to excuse X or muster sympathy towards X would be a mistake. It's possible, but it's not necessary. And before jumping to that conclusion, we should find a reason for it. And lastly, the one that is closest to my Aristotelian heart, confusing kinds of causality. Now, Aristotle himself distinguished 4 types of causes to answer the question why, but some following the Aristotelian tradition have expanded the list slightly. So I'm going to include 6 kinds of causes here, each referring to a different aspect of an effect or event. The efficient cause, the material cause, the formal cause, the final cause, the exemplar cause, and the instrumental cause. And even though modern science left some of these behind centuries ago, understanding them is essential for understanding and approaching many questions raised in disciplines like metaphysics or ethics. Efficient cause is that by which an effect is, the agent or the thing that brings it about, the cause that makes something happen. In other words, this is the kind of cause we generally understand by the term cause. Now, to illustrate all of these, I'm going to take us into the kitchen because all this talking is actually making me hungry. The cook is the efficient cause of soup, the one who makes the soup. The material cause is that out of which an effect is, the matter or material involved in the effect, the stuff of which something's made. Here, soup is made of water, chicken, pasta, garlic, parmesan, etc. It really depends on the type of soup and the recipe. The formal cause is that which an effect is, the essence, the nature, the form, or the structure of the thing, what makes it the kind of thing it is. This can be kind of abstract, pun intended. Let's call it soupness, that which makes a soup soup. The final cause is that for which an effect is, the end, the goal, or the purpose. Here, it's to satisfy hunger. Clearly, the cook wouldn't be making soup if people didn't need to eat. The exemplar cause is that according to which an effect is, the model or design for the effect, an archetype. This would be the soup recipe. And rounding out the list, the instrumental cause, that through which an effect is, the means for producing the effect. Here could be our tools, the pot, stove, the spoon, etc. I think that's a great place to end our discussion of mistakes in causal reasoning, and it's also a great place to end our discussion of induction and science, at least for the moment. Next time, we're going to be changing gears completely. We're going to be going and talking about deductive logic. I've been talking about this for a while. I've been promising that we're going to get around to it. We finally will. And I know it's going to be something that you are going to find incredibly useful. If you can master the techniques, this is actually one of the most practical aspects of a course in critical thinking. Until next time, take care. I'll see you in the next video.